do a little review today on Chapter 12, Chemical Kinetics, in preparation for next week's exam. Before I get started, anything in particular we need to deal with?
Our lab reports are due today, right?
For the last lab, yeah.
Yeah. The calculations, did you want me to type them in? Because I didn't type them in, I was gonna write them in.
In the report?
Yeah.
The body of the report?
Yeah.
It should be typed. The only thing that you can hand draw are graphs.
Okay.
You don't have the capability to do graphs.
I mean, I can type it really quick and go home, but I just didn't know because it came out weak. Like when I was typing it, it was just weird looking to me. I was like, maybe I should just ask it because I don't know.
Are you using Word?
Yes.
Word has a mathematical editor where you can put formulas in.
I mean,
You might have to install it.
Okay, I can hand in a hard copy now and then type that in and send it to you this evening if you want.
You can send it to me on Blackboard.
Okay.
Yeah. By midnight.
Okay.
That's good.
I can do
Good. Okay. Anything related to kinetics that you want to discuss first? Or we'll just take it step at a time. I've got several of these identified in the review document. And this is one of my smaller review documents, I think, because each problem is so intense that I didn't overpack this one. I do want to skip that first one. I mean, try to do that first one. It's like, I've signed up for the Olympics and I just learned how to walk, that type of thing. This is a little too much for our first. So let me skip to number 2. And we'll look at number 2 first. Now I'm going to have to scroll it. Go. Number 2. All right. So remember when we're doing an initial rates, actually multiple experiments required for initial rates. We have separate experiments and we modify the starting concentration for each of the components, each of the reactants in our balanced equation. And then we determine the rate, in this case in molarity change per second. And you recall the reason that these changes are made is so that you can compare 2 experiments where only one of the concentrations varies. Right, so you get this one and this one are the same and that one, and then, well, that doesn't matter. If you skip to this one, the only one that changed is the manganate ion, right? And it produced a difference in rate. So we use that to determine the rate law. First, you need the balanced equation, just like any other chemical problem. And then, let's see, this is number 2. And then you need to write the rate law. And this gives you the form of the rate law, right? The rate equals what? There's a constant, and then there's initial concentration, or actually any concentration of manganate ion to some order, right? That's the order of the reaction, the power of that concentration. And then we have H2C2O4, I think that's oxalic acid. And it has its order, and then we have protons, or hydrogen ions. and has its order. Let's see, N, O. Okay, so we need to find values for that, that, and that. Now the complete rate law is going to have a K value in there, but this problem doesn't ask you for that. So you don't need to calculate it. What we're looking for this problem is the orders, these powers here. Okay, so what do we do first? Well, we set up this rate in terms of what's the rate for the first experiment. You find out which two experiments you want to compare. We're trying to find out the order for this one. We want that one to change and nothing else. We don't want anything, any of these other reactions to change. So we'll use these first two. And I want to put them, I want to ratio them in such a way that the ratio of the rates is a whole number or not a fraction. So I'm going to put this one on top because it's a larger value than that. So the second one would give you, the rate is 8 times 10 to the minus 4 is equal to K. And then whatever this value is, 2 times 10 to the minus 3, right, to the n power. And this one, I'm going to write these in for the first try, and for the rest of them, we probably won't need to. 1 times 10 to the minus 3. And this one is 1, correct? Okay, we're going to ratio that to the first one, 2 times 10 to the minus 4. It's also a K, same K, right? This reaction has only one rate constant, right? Basically, if the temperature does not change. If the temperature changes, then the rate constant will change. So at the same temperature, that's important that this experiment is conducted at the same temperature for each one of these experiments. And for this one, we have 1 times 10 to the minus 3 to the same power, same order, and then these do not change. Okay? So notice what you get. You divide this one by that one, you get what? 4. Okay. And K into K cancels. This one's the same as that one cancels, and that one cancels. So you really only have this one, which is, and if you have two base numbers to the same power, then mathematically speaking, you have 2 times 10 to the minus 3 divided by 1 times 10 to the minus 3. So that power, right? That's a mathematical rule. So this divided by this is what? 2 to the n power. So what n will give you 4 if 2 is the base? N has to be 2. You have to square 2 to get 4. So that means this first one is 2. Okay? So we can say, all right, it could be this one, it could be that one. It could be this one or that one. So the only one we've eliminated so far is C. Can't be C. So then you go to the next one. Which one gives you this one changing and these two constant? Right? It looks like maybe this one and that one. See, these two are constant, these two are constant, and these change. So we're going to do this one divided by that one. Why? Because 1.6 to 10 to the minus 3 is greater than 8 times 10 to the minus 4. It'll give us a positive number. Or this could be written as 16 times 10 to the minus 4. And then the 10 to the minus 4s would cancel. So let's see. We're going to change these. let's erase that. And K's are going to cancel anyway, right? So we'll just leave those alone. And this one is going to be 2, right? Need a marker. Okay, and this one's going to change. All right, so it's going to be 2 times 10 to the minus 3, right? This one's going to be 1 times 10 to the minus 3. And that's going to be 1 and 1 again. These values over here are going to be 1.6 times 10 to the minus 3 and 4, or 8, no, 8 times 10 to the minus 4. Okay? So this one cancels, that one's already canceled, this one cancels, and you have 1 into 2, which is 2, right? So that's 2 to the m. Did I lose anybody yet? Okay. This is that divided by this to the m power. Okay. This one is 8 into 16 is 2. So what could an m be to make that 2? It has to be 1. Okay. So now we can change this one to 1. Or you just leave it off. The fan putting you to sleep. I'm sorry. Okay, so we have out of these remaining 4, this one to the first power is possible. That one and that one. So B and D are still possible. We just have to find out what's this one. Okay. So this is going to be different. That's going to cancel again. We want to keep this one constant. Now we want this one to be the same. And this one to vary. Okay, so which one would give us these two the same? Here, it looks like these two right here. That's the same, doesn't change. That one doesn't change. This one changes. So we have 1.6 times 10 to the minus 3. Or both of them. All right. And this one is, well, with that, we're going to stick to tradition. We're going to put this one first and this one second underneath. This is denominator, this is numerator. So this one will be 2. And this one will be 1. And this will be 2 times 10 to the minus 3 and 2 times 10 to the minus 3. There we go. Okay, so these cancel, those cancel. We have 2 to whatever order it happens to be. I should have picked a different letter. That says it's 0 order. Maybe I should have used let's see, P. How about P? There we go. That's better. Now, what's this divided by this? 1. So what does P have to be? P has to be 0. It has to be a 0 order. 2 to the 0 power is 1. Okay. So what does that mean? That means if we put a 0 right up here, it doesn't matter what that is. It's still 1. So that term disappears from the expression. It's not even in the expression. Okay? Remember, because 0 order equations, rate laws, only have a K value. They don't have the concentration of the reactant. So that means it was between this one and this one, correct? So it has to be D. Okay? So actually our rate law would be written like that. That would be the rate law for this equation. Okay, that was number 2. Let's see, I picked out number 3. Yeah, number 3 is a good one. A little bit missing there. Let me scroll it up. Okay. Number 3 says the rate expression for a particular reaction is rate equals K. And then this reactant to the first power, and this reactant to the second power. Okay? I like to pull things out of the word problem and put them up on the board because word problems are designed to confuse. If the initial concentration of B is increased from 0.1 to 0.3, so this is for B, is increased from 0.1 to 0.3. Okay. What we're looking for is what effect does this have on the rate itself? What change will we see in the rate? The initial rate will increase by which of the following factors? Well, you look at the change here. How many times did this increase? 3 times, right? It increased by 3 times. So the 3 times here is squared, which means the rate is going to be increased by 9 times. You don't see that?
I mean, yeah, when you throw it out.
So let's try another one. It's not up there, but let's say A is doubled. What does that do to the rate? The factor here is first power, right? So if this is double, that's double. If that's the only change we make. Well, if we make both changes, we take this one 3 times change. Let's say we go here. Let's go this one to there. So that's 2x times, right? So what is this? 2 to the first power, 3 to the second power. So that's 9 times 2 is 18, right? So the rate ought to increase 18 times. All right. Let's see. I must have thought all of these were important on that page. We're going to number 4. For which order reaction is the half-life? For which order reaction is the half-life of the reaction proportional to 1 over K? Half-life proportional, that's what that means, proportional to 1 over K. Okay? Well, let's look at the half-lives for each one. If I can remember them. I need a little refresher. Here we go. For 0 order, first order, second order. 0 order. For 0 order, the half-life is equal to what? 2K. This is the initial concentration of A. Okay. How about first order? That one doesn't depend on K, does it? It does depend on K, it doesn't depend on this one. 0.693 divided by K. I believe that's right. Yep. And then the last one, second order, the half-life is equal to 1 over initial concentration of A times K. Okay, so which one is proportional to 1 over K? All of them. This one's proportional to 1 over K. It's like 1 there, and like 1 there, and like 1 there. They're all proportional to the inverse of K. There's no big mystery or explanation there. It just is. All right. Well, I could have looked at useful information, couldn't we? Useful information. Yep, there they are down the right-hand side. Okay, that was 4, 5. Number 5. Okay. If the reaction 2HI yields H2 plus I2 is second order, we're saying that the rate is second order. You're just given that. Which of the following will yield a linear plot? Okay, what are our options? Time. So if we plot concentration here, if it's first order, what do we get? As time proceeds, A decreases linearly. Zero order, excuse me. Zero order. This is first order. This is second order. How do we get a straight line out of a first order? Natural log of A against time. And it will give you a straight line like that. How about second order? Inverse of A. It goes the other direction. So we need to plot inverse of A against time. Inverse of A against time. Which would be inverse of HI against time. If it's a second order. Okay? All right, 5, 6. Okay. See if we can get both of these up here, because I think I'm going to 7 also. 6. Which step is rate determining? Wait a minute. It must be based on some. Oh, okay. I skipped over vital information. There we go. The following question refers to a reaction 2A, and that's diatomic, plus B2 yields 2C. Okay? And what they're saying is the mechanism for this reaction is given. Step one is we take one of these, we got two of them, we're going to take one of those, combine it with this one, and make some intermediate plus one of those. And this one is very slow. Very slow rate. And in the second step, we're going to take another one of these and combine it with the R and make the other C. And this one is just slow. Okay? Which step is rate determining? If we wanted to write the rate law from this mechanism, where would we start? The slowest step is the rate determining step. So we would start with this one. And remember, in elementary steps, you can write the rate law from the balanced equation. Right? We said initially the rate law for an overall reaction has to be determined. I mean, it's experimental. But when you propose a mechanism, you can take the slowest step, and that's your starting point with a balanced equation. You can write the rate law. The problem is, we write the rate law here. Well, okay, the rate law has A and B, but it's only got one A, one B. Right, so we're gonna have to incorporate, we're gonna have to work on it some more. And we did that for, I think we did it in class once. But that was because we had intermediates in this side of the equation. Okay, so the answer would be B. This step is the rate determining step because it is the slowest one. And notice we say that that was slow, but this was very slow, which means it's slower than that one. Right, so you take the slowest step, that determines your rate. And that's one of the determining factors, one of the factors that you use to decide whether your mechanism is valid. You write the rate law from your mechanism and see if it agrees with the experimentally determined rate law. That's one of the things you do. What's the other one that you have to do? You got to add these two together, and they have to be equal to this one. Right? It's Hess's law again. Add these two together, probably this one, yeah. There's two, there's A2 and A2, great, we're good there. There's B2, yep, we're good there. Two C's, yep, we're good there. R on the right-hand side, R on the left-hand side, that intermediate is canceled out. So it meets that first condition. And then the second, like I said, is when you write the rate law from the mechanism, it has to agree with the experimentally determined rate law.
Have some.
Got to keep you busy so you don't fall asleep. And let's see. This is also for 104L. Okay, that was 6. Let's see, we're going to do 7. I got it marked. Let's see if we can tackle this one, make sense of it. Okay. Yeah, this one's gonna take some doing. Do I want to come back to that one? Let me see if there are further discussions that might be more useful before we get to number 7. I think I'll come back to 7. Let's do that. Let's come back to 7 and I'm gonna skip to 8 now. Talk about catalysts and energy diagrams for a reaction. Okay, so with this energy diagram, you have to assume it's an energy. Well, we're told it's a potential energy diagram. It just doesn't label all the axes. This is the energy, and this is progress of the reaction. Could be time, could be anything. But the reaction moves from left to right, reactants to products. And this is the energy transition that goes through each step. Okay, which letter shows the activation energy without the catalyst? This is meant to confuse. If you don't understand what an energy diagram says, then a lot of these letters in here just make your head spin. Right? This is where you start with the reactants. This is where you end up with the products. So notice the difference here. You have a certain energy content for the reactants, and this is the energy content for the products. So the difference between this level and that level is this value, D. That's the enthalpy of the reaction. Is it exothermic or endothermic? Well, the products have more energy than the reactants, so it has to be endothermic. You put energy in that you didn't get back. So that one doesn't answer the question. That's not activation energy. What's this hump represent? That's an activated complex. That's an intermediate step from reactants to products. So you need this amount of energy, total amount of energy here, in order to make the activated complex. Which letter shows the activation energy without the use of catalyst? Well, the activation energy is the amount of energy from your starting point to the activated complex. So C is not it. This is from the baseline. It has to be this one, from here to there. You added energy and made your complex. Remember the collision theory of reactions? Reactants have to collide. They have to be oriented correctly. And they have to have enough energy. That's the activation energy. A is the activation energy for a non-catalyzed reaction. Okay, so that's why A is the answer. How about the second one? Number 9. Which letter shows the activation energy using a catalyst? What's the whole purpose for a catalyst? The catalyst speeds up the reaction. Right? How does it do it? What it does is it reduces the amount of energy required to activate. In other words, the activated complex now occurs here and not here. So less energy is required. It's the same, it may be the same activated complex, probably is, but it occurs by a different mechanism. You know, actually, this is a different activation complex. Come to think of it, it has to be. Because if it's the activated complex that you see up here, that's the pathway it takes. But if it's a different activated complex, it requires less energy. And the catalyst is active in that process. So E is the activation energy for the activation for the catalyst. Another way to look at that is if you're going to speed up the reaction, you can look at energy here and let's see, how do we express this? Number of molecules. So you have so many molecules. What's the other way around? I could draw it that way. No, it's the other way around. So you have numbers here and energy here. So the higher energy is out here. And you usually have kind of like that kind of spread. So you have more are in this range, and you need to have a certain amount of energy here. Right? This is activation energy, non-catalyzed. Catalyzed. Okay, so all of these have enough energy to react. The catalyst shifts that activation energy over to here. So now you have this group. Is that right? You have this group plus that. So you have more molecules with sufficient energy to react, which speeds up the reaction, right? Because what's the reaction rate? It's a change in either reactants or products over time. And if you've got more of them available to react, then you speed up the reaction. Okay. That was 9. 10. Okay. For this reaction, what is that? 2 hydrogen peroxide yields 2 water plus O2. And if we propose a mechanism, right, this is the reaction. If we write it this way, that implies that there's no catalyst. But if we write it with something here that shows some component that we're adding as a catalyst, we didn't do it here because that's the question. Based upon this mechanism, where's the catalyst? What's the definition of a catalyst besides a substance added to the reaction that increases the rate of reaction? Okay. It has to go in and come out seemingly unchanged. So which one goes in and one side comes out the other? That one right there. Iodide ion. So you would write it here as a catalyst. Okay. What's this other one? IO minus, because it's not up here. Right? It's there, it's on this side, it's on that side. That's an intermediate. Right? An intermediate of the reaction appears in the reaction and disappears before the reaction is finished. But the catalyst is I minus. Right? We usually put that in there as potassium iodide, aqueous solution. From that video, I think I showed you the video with the foaming volcano. Mm-hmm. Yeah, that's the reaction they were doing. Okay, 10. Let's see. we're going to skip 11, 12. Consider this reaction. Let's see, overall, you have, what's O3? Ozone. Everybody's heard of ozone. Okay. There's a reaction. This one occurs, well, actually anywhere. It can occur anywhere. But the production of ozone is naturally occurring at very high altitudes. Oxygen is absorbs ultraviolet radiation from the sun and produces ozone. And then the ozone is a much, much more efficient absorber of ultraviolet light. So that ozone layer in our upper atmosphere is protected. But it can't undergo this reaction only usually at those altitudes. As fast as it does this, more ozone is produced by ultraviolet radiation. The problem is we've pumped some things into the atmosphere that act like catalysts. And they catalyze the decomposition of this one, but they don't catalyze the reverse reaction. So when you hear talk about the ozone hole at the poles, that's the cause.
I have a question. They said that hairspray was one of the causes of that. How does that, is it like the aerosol or what is it?
It's probably the propellant. Right? What gas do they put in there to pressurize the can? Yeah. Now they used to, I'm sure they used to use fluorocarbons, hydrofluorocarbons, like Freon. But now I'm sure they don't anymore.
Well, I mean, I don't think it is anymore, but I was just wondering because I did a astrology class and she talked about that a lot. And she was like, actually, it was this women that were just taking it out piece by piece because the hairspray. And I was like, oh.
Used to be. Yeah. Those chemicals have been banned. So now you can't use, let's see. And this was a common one. Right, chlorofluorocarbon was the original Freon in refrigeration systems, and it was notorious for causing that reaction. Now they use other versions and mixtures to as refrigerants that aren't as devastating on the ozone as that one is. They're more expensive, of course. If you've ever had to recharge your car or your home air conditioning system, actually they get more expensive because as soon as they start using a different Freon, type of Freon, the government bans it. So they have to go to another one more expensive to produce. And then any equipment that's built around that Freon, that earlier version, it starts to run out. The supply starts to run out and the price goes like that. So if you've got an old system, there's a point at which it becomes cheaper just to replace it.
When I was in high school, my parents refrigerators started going out and they were just getting more.
Yeah, yeah. I recently replaced mine. My home heat pump, well, it just crapped out at me. It was too old. So I didn't do it because of the Freon. But back to the topic.
Sorry, that was all.
No, that's okay. No, those are good discussions. I'd much rather answer questions than just hear myself talk. Okay, so here's a proposed mechanism for this decomposition. One ozone makes one oxygen plus an oxygen atom. That's also known as a free radical. A free radical is any atom or compound that has unpaired electrons. So that oxygen atom will be, let's see, 8 electrons. Remember from first semester, electronic diagrams? 1s2, 2s2. You remember that?
Yes, now.
Okay. Now you have flashbacks, post-traumatic stress. Okay. And then 2p, let's see, that's 4, have 4 here. Well, this p is subdivided, into the 3, and x, y, and z. And you'll have 1, 2, 3, 4. Okay? So that means these 2 electrons are unpaired. So if we wrote the Lewis dot structure for that oxygen, we would have 2 paired and 2 unpaired. That's a free radical because of these unpaired electrons, and they are extremely reactive. You've probably heard in popular literature and media, you want to take our dietary supplement because it scavenges free radicals in your body. Right? Your body is producing free radicals all the time, and it has mechanisms for neutralizing those free radicals. And the most common way it does that is with polyunsaturated compounds. Those compounds that have double bonds between the carbons. They're effective at soaking up those. So that's why polyunsaturated fatty acids are good for you. And one of the reasons I take 2 gel caps every morning. It's not pure fish oil. I can't stand pure fish oil. It gives me bad taste all day long. But it has vegetable components that have fatty acids. They call them 369s. And biochemistry, take my biochemistry course and we'll teach you about those. You have to take organic first, unfortunately. Shameless plug. Okay, so this is one step. And then we take another ozone, the second ozone, and react it with that free radical and make 2 oxygens. So if we assume the second step of the mechanism is the rate determining step, this is the slow step. And the first step is a fast equilibrium. And they noted that with this double arrow. That means it goes backwards and forwards so fast, it reaches equilibrium almost instantly. So this is a slow one. It only proceeds in significant rate to the right. Which of the following rate laws is predicted by this mechanism? Okay. This takes some doing, and I might have to get my keep me from leading you astray. I'm going to get my work problem here. Let's see, 12, here we go. All right, so remember what I said about, let's go ahead and write these up here too. O3, fast equilibrium yields O2 plus O. And then the rate determining step is O3 to plus O yields 2O2. Okay, first condition, is this a valid mechanism? It has to be, we have to sum them together and equal valid, right? So these 2 together, these 2 here cancel. And then 2 here and a third one there. Right. So it looks like, yeah, it's valid for that one. Sum the equations and you get the overall equation. So that's good. So now what we have to do is write the rate law. So the rate law is determined by this slow step. So if we write the rate equals some K times this one to its coefficient power. We're in the mechanism now, so you can use coefficients. So its coefficient power is that, and then this one, to its coefficient power. Okay, you only use one side of the equation. And we'll write this in terms of the disappearance of reactants. Okay. We can't leave it there, right? Because it's not going to agree with any experimentally determined rate law for this one, simply because it has a term in there that doesn't exist here. We got to get rid of that O. All right. So let's write the rate for this one forward and reverse. So let's see, how are we going to do this? Let's say this one is, its rate constant is K forward, and this one is K reverse, going back the other direction. Okay. So if we do that, then the rate for this one equals the forward times O3. Okay, that's forward. Reverse would be K reverse. Just look at it this way. Now, these are the reactants going that direction. Is O2 to the first power and O to the first power. Okay. So if we ratio these two together, these two rates have to be equal, right? Because it's a fast equilibrium. The forward rate and the reverse rate are equal. That's what equilibrium means. So this one is actually equal to that. Okay. Now, if we got these two equal, we can say, all right, let's divide both sides through by this one. And here. Okay. This is obviously 1. And now we have, let's solve. We got to get rid of this one. So let's solve this expression for that value. Okay. Do a little algebra. All right. If this is equal to 1, then we can say, let's put this one over here on that side. So that one is equal to this expression, Kf over Kr times ozone over O2. And then we'll take, since this one can go in here, this one can go in here. Let's see, I think I've got room to write it over here. All right, so now the rate is this one. This K, this value, which didn't change. And now, what's in here? We've got Kf divided by Kr, and then ozone divided by O2. Okay? So now we can reduce these. That's a constant, that's a constant, that's a constant. We just combine them all into one constant. Right? So this one, and this one becomes this one. And now we have O3 times O3, which is squared, divided by O2. Okay. There's our rate expression because we have terms that are in that equation. Now, if you look at the answers, you see a -1. All that means is that this is in the denominator. So if we move that into the numerator, we just make it -1. Okay?
It's breakfast time.
That's okay. Anything to keep you awake.
I was about to say, and it's keep me awake.
My brother, he and I both have trouble staying asleep when driving long distances. And his solution was he would roll the window down and keep a toothbrush with him. He'd start brushing his teeth. Hey, stay awake. Okay. That one had some chemistry in the beginning, and then the rest of it was algebra. Number 12. Right. Let's see. 13. Okay. Let's see, maybe I can. Yeah. I'm gonna have to get a new pointer. One with a scroll, a thumb wheel, scroll ball on it. And then I can scroll from a distance. Okay. Needs to go a little bit more. Can't see all of our options. Final question refers to the reaction 2A2 plus B2 yields 2C. So before I scroll, let me write that up here. 13. The overall reaction is 2A2. That looks familiar. I think we did that one earlier. Use that equation over there. And then there we go. The very slow step is this one. Very slow. This is the rate determining step. A2, B2. This one's about to crap out on too. According to the collision theory, the activated complex that forms in step 1, which is the slow step, could have which of the following structures? All right. For the activated complex, collision theory says these two have to collide with sufficient energy to form the activated complex. So this activated complex is not going to have R or C in it. It's only going to have A and B. You don't get R and C until you go over the hump and produce products. So we can eliminate anything that has R in it, right? And this A refers to this thing right here, and this B refers to this thing right here. Okay. It's a little off center. There was no way I could center these letters in Microsoft Word to put them up here where they need to be. So we can eliminate this one because it's got R in it and it's got C in it. And we can eliminate, well, let's see, that one didn't go far enough, did it? There we go. E has nothing but C in it, so it's out. Oh, excuse me, C and A. No, that won't work.
And C can be eliminated.
And what?
C, because C is R.
Right, has R in it, right? And D has R in it. The only one that fits is B. A, B, 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 right? Two A's, two B's, and they're starting to form bonds here, which means that these are weakened also. So B is the only possibility. That just tests your understanding of activated complex and the collision theory.
All right.
13, let's see, 14. Yeah, there it is. I guess to keep this thing flowing, I need to shake it occasionally. Which of the following statements about enzymes is incorrect? Okay. If you're a speed reader, you're liable to go through that and think enzymes is correct. And then you'll get the wrong answer. So you have to take your time and read the question for what it's asking. Which one of these is incorrect? Okay. This one says all of them are correct. Right. So that's a possibility. Right. Ignore that. Okay. Pay no attention to the man behind the curtain. Okay. Incorrect. They are proteins that catalyze specific biological reactions. For the most part, yes. Okay. And as far as we're concerned, that's correct. But if you take my biochem course, you'll learn that there are some catalysts, enzymes, that are based upon RNA, right? And not just proteins. Most of them, a vast majority of enzymes are proteins. Several hundred are now known. Well, that has to be modified too. It's true, several hundred are known, but the number is much larger now than when this document was first prepared. So we're going to have to say that one's true and that one's true. The molecules they react with are called substrates. That is definitely true and hasn't changed ever. The enzyme combines with the substrate, and then the substrate is modified during the reaction. They are equal to inorganic catalysts in efficiency. That is patently false. Enzymes are just orders of magnitude more efficient than inorganic catalysts. Inorganic catalysts, you can expect maybe 1% efficiency. In other words, when it enters a reaction, it has 1%, if you're lucky, of the reactants produced products. I mean, that's better than the non-catalyzed reaction, but it's still not as good as enzymes. Enzymes are, some of them are 90%. I mean, if you get an enzyme in that solution, it's going to produce a reaction almost every time it encounters a substrate. So D is the incorrect one. Something else about enzymes, they're controllable. The only way you can control an inorganic catalyst is sometimes concentration and then temperature. Temperature will affect a catalyzed reaction like it will a non-catalyzed reaction. But with enzymes, you can control the action of an enzyme not just by concentration and temperature, but by secondary activators. Some enzymes just sit there and they do not work unless there's a cofactor attached to them, which activates the enzyme and it works. And if that disappears, that's a control mechanism. They also respond to concentrations of products. And an increase in the number of products will change it, will cause a change in the conformation of the enzyme, which will inactivate it. Also, they usually work only in one direction. Now, there are exceptions, important exceptions, as a matter of fact, to that rule, but many of them only work in one direction. So if you want the reaction to go reverse, you need a different catalyst or a different enzyme. So it's all about control. If you let these reactions run wild inside your cells, you won't be living very long. Right? The enzymes are absolutely essential to proper functioning of a cell. Okay, let's see. What do I want to do next? 14, 15, we've done one like 15 before. Well, 15 does ask you to determine the value of the rate constant. But I've worked it out in the review document. If you have any questions about that one, we can talk about it. Let's see, 15. It takes some doing. I'll tell you what. I'm going to skip down to the part where we determine the rate constant. We've determined the order for each of the reactants. Here, that one, that one, that one. Right. And we do it the same way we did that earlier problem. We just look for, right? I would use this first one to determine the order for selenous acid. Right? Because that one changes, that one doesn't, that one doesn't. And then for this one, I would use, let's see, we want this one to change here to here. That would do it. How about this one? Changes from here to here. This one's constant here, this one's constant here. So I'll use these two to determine that order. And this one, we need, let's see, this one and this one, right? The fourth one and the last one, because these don't change and these don't change, but these do change. And that'll give you, by that same method, initial rates, will give you the order for each of these components. So now let's write the 15. Let's write the expression for the rate, not knowing that one yet. So this is selenous acid. Let's see. We determined one here, and this one, iodide ion, is 2, and protons is 3. There we go. Okay. So we went through that whole process and we determined that this was the rate reaction. Now we want to find what's the K. Actually, this is the simplest part of the whole operation. To do this one, all you need to do is pick one of your experiments, plug in the values for that, and that, solve for this one. So I think the example I used here was experiment 4. This one right here. So the rate is 6.66 times 10 to the minus 7 equals K. And then the concentration is 1 times 10 to the minus 4 to the first power. And then iodide is 4 times 10 to the minus 2 squared. And then protons is 2 times 10 to the minus 2 cubed. Okay? So this one doesn't change. That one squares, that one cubes. And then you multiply those all together and divide them into this one. And gives you your K. And if I did that right, the K should be 5.2 times 10 to the 5th. I'm sorry. Oh, I scrolled accidentally. There we go. Now the units of measure, well, I put them in this document, but you don't need to here. If you're very careful about your calculations, then all we need is the number. Because with different orders and concentrations, you can get units of measure can just be all over the place. Okay, so that's how you get the K. Once you've got the orders, you just take one of the experiments and plug in the values and solve for your unknown. All right. 16. Let's see. There it is. Okay, for this generic reaction, yield products. The initial concentration of A is given as A0 equals 4.2 molar. Okay. The first two half-lives are 56 and 28 minutes respectively. Calculate K. Okay. When I'm confronted with something like this, I do the same thing as always. I extract information from the problem and put it up here, but how you want to put it up here is important. I want to make a table. If I'm going to determine half-lives and use that information, I want a table that shows me the real experiment that gave me that information. So I want concentrations of A in this one. And then at what time did that occur? Actually, concentration here. Actual concentration. So at time 0, right, the concentration was 4.2 molar. What was the concentration at 56 minutes? Half of it, right? That's the first half-life. So the concentration has to be 2.1 molar. Okay, how about the second half-life? What would the concentration be after another half-life? When you say half-life, second half-life, now you're starting from here. And half of that is 1.05 molar. But what's the time? Well, the half-life was 28 minutes, right? So between here and here is 28 minutes. But what's the actual time? 28 plus that. So that's, let's see, 84 minutes. There we go. Now I've got the experiment up here on the board in front of us. Calculate the K. All right. Here's the approach I would take. Process of elimination. Half-lives. So if we say, what's the half-life for 0 order? The half-life for 0 order is A0 over 2K, correct? The half-life for first order is 0.693 over K. And second order is, let's see, one over A0 times K. Is that correct? Scratching my head. Yeah. Yeah, that's right. Okay. So the approach that I took when I worked out the problem there, which is an ancient one, is I plotted this data. I said, okay, if we plot the data against these values, and I get a straight line, then it's this one. Right? If I take the natural log of this one and plot it and a straight line, then it's this one. If I take the inverse of concentration and plot against time, then it's this one. And then you just use whichever one is appropriate to solve. But look, there's really a simpler way. Ask yourself, which one of these half-lives do that? Well, actually ask yourself, does the half-life depend upon the initial concentration of A? So this is the initial concentration of A for this half-life, 56 minutes. This is the initial concentration for the second half-life. It's a different value, right? So the concentration does matter. What does that mean? That means first order can't be, because it doesn't depend upon the concentration, correct? So now what we do is we say, all right, let's assume it's zero order. That's a mess right there, isn't it? Say zero order. Let's take this one and determine K with each of these half-lives. So if we take this one, zero order, and calculate the K for this half-life, then this one would be 56 minutes equals concentration of A, which is 4.2, divided by 2K. Right? Okay, so what's K? Let's bring K over here. So 2 times 56 is 112, divided into 4.2. Let's see. Where did I say? Okay, over here, yeah. 4.2 divided by 2 and then divided by 56. 3.75 times 10 to the minus 2. So K is equal to 3.75 times 10 to the minus 2. Now let's take the other half-life, 28. And its starting concentration is 2.1 times 2K. So this one, K is equal to what? Let's see. K comes over here, 28 goes over there. So 2.1 divided by 28 and then divided by 2 is 3.7 times 3.75 times 10 to the minus 2. Okay, actually we solved the problem. We determined that it's zero order. And the value is 3.7 times 10 to the minus 2. How do I know that's true? Because K is a constant. If these were two different Ks, then we'd be barking up the wrong tree. But since we started here and we ended up with both Ks equal, that means this one cannot be it. We can go ahead and do this one and prove, right? But if you're in the middle of the test, you want to find the right answer and move on. So this is the right answer. It's zero order, and the K value is this one because they're both the same for these concentrations. And that's because this K is equal to that K. That's why they call it a constant, because it doesn't change. Okay? So I think that's a better approach. I mean, the solution that I give you in the worked problems is true. Right? That determines which one is which based on this data. But that requires that you draw a graph. But this one only requires that you process of elimination. And I think that's a better approach when you're short on time and resources. I probably ought to go in and maybe supplement this one or change it entirely. Okay, let's see, which one do I have marked off next? 17? 17, I'm gonna do 17. Um, hmm. The solution I gave here, you have to draw the graph. All right. I wouldn't do that to you on a test because you don't have the facilities to draw it. Right? So what I would do is, if I took a problem like this, I would say, okay, given this problem, this set of data describes a first order reaction. Then you know how to write the rate law. Let's see. Okay, dead air. That's not good. Fortunately, we're not broadcasting. Thank for airtime. Okay, if I tell you that it's first order, okay, we're using the integrated rate law. That's what we're doing. Okay, and that's in your useful information. Okay. Look back here. For a first order, the integrated rate law is the natural log of A equals minus KT plus log of A0. That's what I would do. Then you would say, let's see, before I do that, um, 17. Let me scroll a bit. That's not the one I was thinking of. You know, because so what's the question? The question for 17 is, oh. Okay. What am I doing? There should be a line drawn right there. This is for the next question. This one refers to that one right there. Okay. So let me scroll down a little bit. Oh, my goodness. All right. So for this equation, oops. 2N2O5 gas yield 4NO2 gas plus oxygen. Okay, and we have that set of data for this reaction. At time 0, we start off with this concentration. That's N2O5 sub 0. And then we measure at time intervals. Okay, do that, do that, do that, do that. And rather than, and the question is, the initial rate of production of NO2 for this reaction is what? Right? So that you don't have to go in and graph it and determine that it's first order. I'm going to say that this is first order reaction, period. So that gives you your new starting point. All right. So now that we know it's first order reaction, the integrated rate law incorporates time. Right? Whereas the differential rate law does not. Right? It's just K times the concentration to the order. So we need something that incorporates time, and we're going to use log of N2O5 yields minus K time, is your time factor, plus the initial concentration, the log of the initial concentration. There we go. So in order to determine the rate, the initial rate, we have to know the K, right? Because if we write the rate in terms of right, we could write the rate in terms of this. Actually, we do need this one first because the data is in terms of N2O5. So we have to write this one as the rate equals K times N2O5 initial. And we're told it's first order, right? Okay, so that's the rate law. We want to know this rate at the very beginning. So that's where we want this concentration to be 1.24 times 10 to the minus 2. But we got to find out what K is. Okay? So, what we need to do is say, all right, let's take out variability as much as possible. So how do you do that? Well, you spread your calculation over the entire group. If you just use this equation between those two or those two or those two, you might introduce some error. But over time, you're going from here to here, you've smudged out most of the error. So the time interval here is 70 minutes. So we're going to make this one 70 minutes. The initial concentration is 1.24 times 10 minus 2 here. And what's the final concentration? Well, that's 0.15. 0.15 times 10 to the minus 2. Okay. Now that puts a value here, a value here, and a value there, and there's your unknown. So you can solve for K. And if you solve for K, you should get 3.02 times 10 to the minus 2. Okay. So if we write the rate law in terms of this value, well, what is the rate at the beginning? Right? The rate of disappearance of N2O5 is equal to K, whatever the K is, which is this one. Let me just do it this way. rate equals this one times this one to the first power, and the initial rate we want is this one right here, 1.24 times 10 to the minus 2. There we go. So now we can calculate the rate at 3.74 times 10 to the minus 4 molarity per minute. Actually, it's units of measure. But this is for N2O5. N2O5. Okay? So to answer the question, what effect does this have on that one? The initial rate of appearance of this is twice this one because it's 4 to 2 or 2 to 1. So we should double this rate. So as this one disappears, twice of it shows up over here. So this would be 7.48 times 10 to the minus 4 molarity. This is in terms of NO2. So that's why the answer is this one right here. Actually, it should be 7.5, but that's the best answer. If you show me your work and you say none of these based on that, right, then you'd be right. If you don't show me your work and just pick one, then I have to assume that should have been this one. If you pick that one, but show me your work, and you can argue this one is the correct answer because 7.48 is not 7.4. Okay. That was 17. Let's see, how are we doing on time? 9:30. Let's see. I always have to check myself. 10:50. Okay. We're in good shape. 18. 18. Did I pick up enough of it? Yeah. This question refers to this information. Okay. $18. Okay. The basic information that we're given is the rate constant K for the reaction shown below is 2.6 times 10 to the minus 8. Rate constant equals 2.6 times 10 to the minus 8. Molarity, liters per mole second, liters per mole per second. Like that. Because this second is in the denominator, we left it alone and we put this as molarity. When the reaction proceeds at 300, the temperature here is 300 K. Okay. The activation energy is 98,000 joules per mole. So the energy of activation is 98,000 joules per mole. Let's see, universal gas constant here. All right, that's given to us. So we'll just write it in here also. 314 joules per mole. Okay, I think we wrote this one in terms of moles per liter seconds because of all these moles in here. So if we need to cancel any of them, then we've got that value already. And this reversed to this equation. 2NOCl yields 2NO plus Cl2. Okay. That's our starting point. This is the K for that temperature. With activation energy here, universal gas constant there. if the temperature is changed to 310 K, now the temperature is 310 K. The rate constant would change. Well, yeah, obviously. The ratio of K at 310 to K at 300 is closest to what whole number? So we're looking for the ratio. What is the ratio of K at 310 to K at 300? That's the question. All right. We're talking about Arrhenius equation. And probably the best form of that equation for this process, although you could use the differential form, which is a little unwieldy, but it's workable. But the integrated form is a little easier to deal with. So, what does the integrated form look like? Let's see, is that in your useful information? Should be. Arrhenius integrated. Yeah, it's the bottom equation on the right-hand side of the page. Log of K2 over K1. So we're going to use the second, this is K2. Right, well, the temperature assigned to K2. So the log of the K value, 310 over K 300 equals what? Well, we need the activation energy. I'll just write this in here. Divided by R. And then we have 1 over the lower temperature, T300, minus 1 over T310. Okay. So let's put some numbers in here. We're given the activation energy is 98,000. This thing's going as long as possible. 98,000. And this has to be in joules because this value is in joules. 8.314 joules per mole. Okay. So this one has to be in joules per mole. Okay. So notice this joules per mole, that joules per mole cancel. And that means 1 over 300. And this has to be in units of temperature K, 310. Okay, so we just need to subtract that one from that one, multiply it by this one. This is K. These are actually reciprocal Ks. So these reciprocal Ks cancel that reciprocal K. And you have a dimensionless number over here. And that's fine because the values of K here cancel values of this little k, constant K. So this is dimensionless too. But all we want to know is this one right here. What's the relationship? What's the ratio of K at the higher temperature to K at the lower temperature? And if we resolve this value in here, we get 1.2675. 2675. Right? So how do we get this value? Well, we take the anti-log of this, right? Which is actually this. K over 310 divided by K 300 equals E to the 1.2675. That's the anti-log on your calculator. $1.2675. And then here's my e to the x, 3.55, or that's the exact number, 3.55. Nearest whole number is 40. Right here. Okay? So the real meat of this problem is understanding that you need this equation right here. Arrhenius relates two temperatures and two Ks at those different temperatures. If you know the activation energy. If you don't know the activation energy, but you have calculated the Ks for these two temperatures, then you can find out what the activation energy is for that reaction. And this is without a catalyst. If you stick a catalyst in there, then that's going to change. And you have to specify for that reaction. Okay, that was 18. And now we're coming down. I did skip that earlier one. I'm not sure whether we need to go over that one or not. We'll take a look at it. Let me see what's left. You break? Oh, throw away trash.
Well, I'm gonna use that one, not you.
Okay. Let's see. That was 18. Scroll for 19. Let's see if 19 is something new, different. Second order, given the second order reaction of NO plus O3, ozone, yields NO2 plus O2. The rate constant is measured here at 298, and the activation energy is measured at 11.4 kilojoules per mole over the temperature range 195 to 304. Okay, what's the rate constant at 233? All right, this is an application of the Arrhenius equation. You just fill in this term as the activation energy, but it has to be converted to joules. Right? This is kilojoules. So it'd be 11,400 joules per mole is the activation energy. The initial temperature is what? Well, 298 is the initial temperature here for that K. Right? And this is the new temperature, 233. So we're actually decreasing the temperature. And then you solve for the other K. Right? So we use the same equation we did in 18 to solve this one. Let's see, which one did I say was T1? Okay. So let me take a look at that formula again, because it's important you get them in the right order. K2 on top. For 19. We're going to use the Arrhenius equation again. K2 over K1 equals activation energy over R, and this is 1 over T1 minus 1 over T2. So depending on which one you pick, the initial would be T1. So the initial temperature is 298, right? 298 K. And the final is 233 K. So this temperature 1 has to correspond to that K. And that K was determined at 1.08 times 10 to the 7th. 1.08 times 10 to the minus 7, no, to the 7, divided by K2. That. Then you have this value, which has to be, well, just write it, 11,400. Because the R is in terms of joules, then this one has to be converted to joules. It's kilojoules up there, but it needs to be joules here. And then we insert 8.3145. Let's crap it out. Then this one will be 1 over 298 minus 1 over 233. It's important to get these in the right order, corresponding to the correct values up here. Otherwise, you get the wrong answer. So we'll have a calculation here, will give us a number. How do you deal with this one? You need to understand how logs work. So the log of a quotient is actually the log of the numerator minus the log of the denominator. And then whatever that happens to be. This is where you get tripped up. Well, two places will trip you here. One is make that conversion. And two is, what do you do with this log expression? And that's what you do with it. Right? That's what logs mean. That's a log rule. And now you've got an unknown. Right here, you just resolve that. And since it's negative on this side, it'd be positive over here, add it to that, and then do your anti-log calculation, and you got the answer. Let's see. 20. Okay, 20, and then we can backtrack. Let's see. There's 20. The first order decomposition of hydrogen peroxide at minus 30 degrees occurs with a half-life of 42 seconds. What will be the residual concentration of 10.2 mole per liter hydrogen peroxide after 3 minutes? All right. Let's see. Okay. Yeah, a lot better. Okay, so here's what we know. Decomposition, first order decomposition of H2O. H2O2. First order decomposition. In fact, we don't have to know what the products are. We're working from this decomposition to produce products. In its first order. So first order means what? Well, if we want to know if we want to see a straight line, we need the log formula. Minus KT plus log H2 initial. There we go. So why do I want to use this one? Because the question is, what will be the residual concentration? What's left over after you start from this concentration, 10.2 molar. So if we start with 10.2 molar here, we want to find out what this one is. But we need to know both this and that. So this one is going to be 3 minutes, right? Or 42 seconds. So 3 minutes is how many seconds? 3 times, 3 minutes times 6 is 180 seconds, right? So this is going to be 180 seconds. We need to know what K is. Okay? A half-life of 42 seconds. So the half-life of 42 seconds, if we draw this like we did before, H2O2 time, right? Zero concentration is 10.2. And then the first half-life at 5.1 is 42 seconds. Okay? So if this is first order, we got to find out what K is. And K says that the half-life is equal to 0.693 over 2K, correct? Is that right? No, it's just over K, excuse me. Just over K. Okay. So the half-life here is 42 seconds. Equals this divided by K, so we just have to solve for K. Right? K equals 0.693 divided by 42. Right? So that gives us our K that we need to solve this equation. (1.65 times 10 minus 2). Okay, so all we have to do is put that one in here. There, times this amount, is that, and solve for that one. So what's the log of 10.2? It's 2.3224. 2.3224 is this one. This one is 180 times 1.65. Let me scroll up. There we go. 180. So this is 2.97 here. That's a minus. So a minus 2.97, and a plus 2.3224 is minus 6.476 times 10 to the minus 1, and that's equal to the log of H2O2. Right. So now we just have to e to that power. And I get 0.52. So the concentration after 180 seconds equals 0.52 molar. There it is right there. Actually, I did get 3. 523. So that's how you solve that problem. The only way that you can get there, because it says after so many minutes, and it's first order, you have to have the integrated law because that's the only one that has a time factor in it. Can't use the integrated law, differential law, because it doesn't have time. The integrated is the only one that has time. And then once you plug in what you know, and what you want to find out, you find, oh, I got one missing information here. So then you got to go out and say, all right, how do I find that? But you get it from the half-life. All right. And that was the last one in the group, but we skipped a couple of them simply because they were too much for the time. let's go back and pick up. Let's go. I never had identified a number one as one that we wanted to do. Why did I do that? Oh, because it was a stupid problem. Yeah, you had to make any number of assumptions in order to get there. So that's why I threw one out. Okay, so we don't do. Let's go back to 7. Seven might be worth looking at. It goes on forever. Let's see. All right, let's back up. See if I have to scroll or if I can just page. There we go. All right. So let's stump the band. The reaction 2NO plus O2. 2NO plus O2 yields 2NO2. Is that right? 2 nitrogens. 2 plus 2 is 4. That's right. And it obeys the rate law. Change in O2. The rate, okay. We're referencing this in terms of the rate of disappearance of O2. That's what negative means. It disappears. And that makes sense for this reaction. As the O2 disappears, the rate of O2 disappearance is equal to a K value times the initial concentration of O2, second order in O2, excuse me, and first order for O2. Okay. So which of the following mechanisms is consistent with the experimental rate law? All right. So we need to look at this first to see if we can eliminate any of these based upon brain farts. Do they add up to this equation? Do they add up to this one? Right. And we check them. 2 NOs here, O2, 2 NO2s. These are intermediates that disappear. That's correct. 2 NOs here, 2 NO2s, NO3s disappear. That's good. 2 NOs and NO2, and there's another NO2. This intermediate disappears. This intermediate disappears. And 2 NO. Oh, NO2 here. No, it's not right. I think this one goes out because it doesn't meet first condition. Is that right? Am I missing something? 2 NOs, N2O2 cancels. And here's an NO2. We need another one. There's another NO2. This one cancels. That NO is on the same side as this one. So this one can't be in. Right? It doesn't meet the condition, the first condition. We throw that one out. How about this one? There's an NO, there's an NO. There are 3 O2s on this side. There's 1, 2, only 2 on that side. So we got an O2 on this side. That's okay. And then an NO and an NO on this side. 2 NOs. That's okay. We need those 2 NOs. And NO2s, we need 2 NO2s. Okay, that one satisfies. So we throw C out. And now it's a battle between A, B, and D. So what we have to do is say, which one of these, based upon the slow reaction mechanism, step, which one satisfies? Okay, so for A, the slow step is NO plus NO yields N2O2. Okay? All right. My guess is this one's not going to work, because if we write this equation in terms of the reactants, the only term in there is NO. Two NOs, right? We write that rate in terms of these NOs, it's going to be squared. Nothing else. There's no O2s in there. So that's probably not it. How about B? B, the slow one is NO3 and NO. N rate equals NO3 to the first power and NO to the first power. Okay, that's possible. But we got to get rid of that NO3 because it's nowhere up here. So that might be it. Let's look at that one in more detail. Here's a fast equilibrium. This is kind of like the one we did before. Let's see. Yeah. So if we say this one plus O2 is a fast equilibrium with NO3, then this K forward and this K reverse are equal. The rates are equal. So if we write an expression for this one, then it should be equal to the rate of the expression for that one. So this one would be K forward NO02 and K reverse times this one NO3. There we go. Now, if we've got this term up here, we've got to get rid of this one, NO3. So we need to move this one over here, that one, this one comes over here. Now we can plug this one into here. So now the rate becomes this expression, KF over KR NO02 times NO. Right? Plug this one in here. All right, so that gives us, let's see, wait a minute. I left the K out here, excuse me. So that gives us another K here, and these, like that earlier problem, become the overall K. And this becomes NO squared. And this becomes O2 to the first power. That's it. Right there, that's B. Okay. If we did this one, we'd have nothing but O2s, and we'd have to go through the same process. Actually, we couldn't do it. Not the same way, because there's no fast equilibrium in here. We've only got one direction. So we could go through it and try it, but more than likely it's not going to work because we've already found the answer. It's B. Okay, I think that's it. all the ones that I had marked.